This video discusses computer systems and digital electronics. So we'll just discuss basic computer systems, and then we'll get into digital numbering systems, and we'll also look at some binary logic circuits and discuss programming. All right. Computer systems are digital devices. Okay, a digital device or a digital circuit uses electronic switches, usually known as transistors, to switch between a high voltage and a low voltage. And so inside of the computer, what we're talking about is actually a voltage. So if it's a high voltage, we consider that to be a 1, and if it's a low voltage, we call it 0. Now, 0 doesn't necessarily mean 0 volts, but it means very, very small voltage. And so inside of the computer, and again, the robot controller is really just a digital computer. Okay, so when we're talking about digital computer, the controller of the robot is a digital computer. And so what happens is that as the computer is processing data, the data is switching between highs and lows. So there's a clock associated with the digital computer. So the dotted lines in this graph here kind of indicate when the clock signal appears. And so this is like a string of ones and zeros that might be being sent from one place in the computer to another, or it could be from one digital computer to another digital computer, like from one robot sending a message to another robot. And so when the clock signal occurs, that's when the value is read. Is it a 1 or a 0 at that time? So this is a simple transistor circuit showing kind of what would be happening inside of the computer. This is a NPN bipolar transistor here labeled Q1. So this right here is actually the transistor, and we of course have a voltage source. V1 is a voltage source, and then we have a switch. Now this switch it looks like a manual switch that we can actually toggle, but inside the computer it would actually be another transistor. So what happens is when this switch is closed, you get a high voltage on this circuit, so you get current flowing down through this circuit into this transistor, and you see that arrow there. And the current is going to be flowing in the direction of that arrow. So current flows through this and turns this transistor on. When this transistor here, Q1, turns on, what that means is that the voltage between the 2 points right here goes to a 0. Okay, so this type of circuit is actually an inverting circuit. So when this switch closes, then that turns Q1 on, which actually sets it to a low voltage. It's not a 0 voltage, but it's a very small voltage, usually about 0.2 volts. And therefore this signal here, the L1 stands for a light. I don't know why it says 12 volts there. Don't worry about the 12 volts. 12 volts should be over here at V1. But this is like a light or another transistor or something, but the voltage goes low in this transistor, which means that the voltage at the light is low, and therefore it would be off. And then when the switch is open, then what happens is that this transistor turns off. Well, if the transistor turns off, then the voltage can flow down through the resistor R2 and into the light and turn the light on, and that would make the light would be an on or a 1 when this transistor was off. So again, this is an inverting type of circuit the way it's drawn here. So when this transistor is on, what happens is because this voltage is so low, then the voltage across the LED is also low since they're connected together, and so the light would be off. But remember, inside, the important thing here is to simply remember that inside of a computer, low voltage is considered off or 0, and a high voltage is considered on or 1. Alright, so I already kind of went over the circuit. So to represent these highs and lows, we try to use a numbering system. So because the reason we need to do this is because we don't just have one transistor in the controller. We actually have literally millions of them, but they're usually connected in either groups of 32 if it's a 32-bit computer, or a 32-bit controller, or 64-bit if it's a 64-bit. And so what we need to do is we need to string these together, and so we use numbering systems for that. Now, we're all familiar with the decimal numbering system, and the decimal numbering system, the one that we've been using since we were born effectively, is decimal, and deci stands for 10, right? Deci is a prefix for 10. So what that means is that we have 10 characters. But notice that 10 is not one of the characters. We have character 0, which is effectively a placeholder, and then we have the characters 1 through 9. So when we're counting up and we get to 9 and we try to add one more to 9, what we have to do is we use the placeholder. We put 0 in the 1's place, and then we can put a 1 in the 10's place. So that's how we count. Now, computers use what we call the binary numbering system, which means that they only have 2 characters. And again, the reason for this is because inside there you can either have a high or a low. You can't have a whole bunch of different values in between. It's either a high or a low. And so therefore we represent the high as a 1 or the low as a 0. So these are our only 2 possibilities. And so we have these 2 characters. So if we wanted to count and we were at 1 and we wanted to add 1 to it, what we have to do is use our placeholder in the 1's, and now we move to the next column. But in this case, the next column is going to be the 2's column instead of the 10's column. And so 1, 0 in binary is actually the number 2. Okay? So, as I said, so we have either a 1, which is a high voltage inside the computer, or a 0, which is a low voltage. And sometimes we also use true or false for these. I didn't put that in the slides, but so a 1 is on or true or a high voltage, or a high, simply a high. And a 0 is off, low voltage, or a false. Now the binary numbering system, again, just uses 2 symbols. Okay. And so when we string these all together, again, like if I have a 32-bit controller, then I'm gonna have 32 of these 1's and 0's all together. If I have a 64-bit computer, I'm gonna have 64 1's and 0's all strung together. And so it's just very, very hard if you try to imagine reading this number here. With all these 1's and 0's in here, it's like, what is that number? Okay, computers can read that number very, very easily. They can understand every single bit immediately, but humans, we look at that and we can't even type it again or write it down without probably making a mistake, because we get, is that 6 zeros? Is this 6 zeros in a row? Is there 5 zeros in a row? And my eyes are starting to run together. And so we use some different numbering systems to help us relate to those. And so, the decimal numbering system is good, but the problem with the decimal numbering system is that it doesn't relate one-to-one with every single one of those ones and zeros. So we have two other numbering systems that you'll sometimes see inside of digital computers, and that is the octal numbering system, which uses 8 values, right? Oct is the prefix for 8. And so that means it uses 8 values. Now those 8 values are 0 through 7. But the nice thing about the octal system is that it has a one-to-one relationship with 3 bits or 3 binary, 0, 1, 0 or whatever inside of the digital computer. Now octal was kind of fell out of favor. On the older computers, it was used extensively, and you still see it once in a while, but most of the time now you'll see what we call hexadecimal, which is 16 values. Well, the only problem with hexadecimal is the fact that we know with decimal we had characters 0 through 9. So when they decided they wanted to display 16 unique symbols in one spot, all right, they decided that, okay, well, I'm going to use 0 through 9 like the decimal system does, but I still need 6 more, and so we just use the first 6 letters of the alphabet. Sometimes you'll see them in lowercase, but usually they're preferred to be in uppercase. But these 6 values now added to our base characters 0 through 9 give us 16 unique symbols. So the hexadecimal system uses 16 unique symbols, 0 through 9 or A through F. Any of those are a valid digit in a hexadecimal number. But what's nice about the hexadecimal numbers is that we can represent 4 bits, 4 binary, a string of ones and zeros, 4 ones and zeros thrown together can be represented with one hexadecimal symbol. And so that's why we like that, because we can read it as humans, we can read it much better. So here is an example when you're counting, right? So I started out with the decimal because we all know how to count in decimal. So we have 0, you add 1 and you get 2, you add 1 to that and you get 3, and then I skipped ahead. So it's 7, you add 1 to 7, you get 8. You add 1 to 8, you get 9. You add 1 to 9, and this is where we have to put in the placeholder 0, and then we carry over into the new column, right? So 9 plus 1 gives us a 0 in the first column, and then we put a 1 now in the tens column, all right? And then so on. So if we go on and we go down to 14, 15, 16, and so on. Now, if we get all the way up to 99 and we would add 1 to that, then we would get down here and we would have to have 1, 0, 0. So we would have to put a placeholder in the ones column again, and then we would also have to put a 1 in the tens column, and then we would end up with 100. So we have the hundreds column. Now, in binary, what's going to happen here is we do a 0, 1, 0. We do a 0, we do a 1, we add 1 to 1. Now we're out of characters, so we have to put the placeholder in and move to the next column. All right. So so if we do 7, 7 would actually be simply 3 bits, 1, 1, 0. Okay, so we'd actually have to already be up to 7 would be 1, 1, 1. Excuse me, 7 would be 1, 1, 1. And now if we wanted to count to 8, so we wanted to add one more here, and we wanted to go up to 8, we're going to have to move to the next column. So again, we have a 0. Now this is the 1's column right here. This is the 2's column. This is the 4's column. And this one would actually be the 8's column. Okay. And so we would have to add that extra character. And so, but then when we went up to 9, we would just add one more in there. And then when we went to 10, we would have 1 here in this column, plus 1 would give us a placeholder of 0 in the 1's column, and add a 2. So here we have the 8's. This is 8's. We have 1 8 plus 1 2, which of course is 10. All right. When we get up to 14, we would have like a 1 1 1 0. And then 15, we would add 1 to get that, and that would give us 4 1's. All right, but now we have 4 1's. If I add one more to that, then I'm going to have to put a 1 in the 1's column, or excuse me, a 0 in the 1's column, a 0 in the 2's column, a 0 in the 3's or the 4's column, a 0 in the 8's column, and I put a 1 in the 16's column. So this is the 16's column here. All right, so we actually have to move to the next column again. All right, so you can see these strings of 1's and 0's just keep getting longer and longer. So we already have 5 1's and 0's strung together just to display a value of 16. All right, in binary, to display 16 decimal in binary, it's going to be 1 followed by 4 zeros. So these just kind of keep going and going and going. So if we try to display that in Octal, then with Octal we can go up to 7. We can go through 0 through 7. So we have 8 unique characters. The last one is 7. It's not 8, it's 7. But again, the nice thing about Octal is it represents 3 bits in a string. So here 0 would be 3 zeros in bits. 1 would be 0, 0, and a 1 in the 1's column. All right, and so 2. Now when we get to 7, 7 is our last unique value in Octal. So what we're going to have to do is we're going to have to put a 0 in the 1's column. This is always the 1's column, no matter which numbering system you're using. But we have 0 in the 1's column, and we put a 1 in the 8's column. So now this is the 8's column here because we're in Octal mode. So this is the 8's column. So we had to move over to the column. But now notice here that this 1 represents 3 bits, 0, 0, 1, and then the 0 represents 3 more bits. So at this point, even though we only have 2 digits here, in binary we're representing a total of 6 bits. Okay, 3 for each digit in the octal numbering system. All right, and if we count up 11, 12, okay, and now if we go on up and here I guess We wanted to count 14 and 15. Okay, so this, or no, that was correct. I'm sorry, this was 16, and this is 17 because I'm counting octal. Sorry, I got confused. I was wondering why I had 16 here. So 16 in octal is 14 in decimal. Okay, but again, it's representing those bits. So if you look at the binary bits, we have 6 binary bits being represented. So we have a 001 and then a 110. Okay, and then in the 17 is representing in binary 001 and then a 111. And then 20 in octal is 16 in decimal, which represents a 010, which represents a 010000. So it's representing, again, 6 bits. Okay. So hexadecimal now, we can go up to 16 unique characters. So as you look here, you go 0, 1, 2, 7, 8, 9. When you get to 10, okay, when you get to 10 in decimal, we're going to start using the letters. So 10 in decimal is A in hexadecimal, which is also 1010 in binary. So again, each of these characters, even this like 0 up here, this single digit 0 in hexadecimal, is representing 4 bits inside of the computer. E, the symbol E in hexadecimal represents 1110 in binary, which of course is 14 in decimal. And F represents 4 ones in a row in binary, which is 15 in binary. And when you try to go to 16, now we have to put a 0 in the ones column. Again, this is always the ones column, but now we put a 1 in the 16s column. So now we're representing 8 bits. Okay, so these 2 digits in hex represent 8 bits. Now if we were to carry this on up here, let me just rearrange this a little bit here. So if we were to carry this on up here, so that if we had 1F, for instance, 1F would represent 001 and then all ones. And so then this would actually be 31 in decimal. And then we would go to 20, 10,000, which would be 32 in decimal. All right. So if we get up to FF, okay, which is all ones in binary, that would equal 255 in decimal. So just as you start getting higher and higher here, those values actually start adding up very, very quickly. All right, so again, humans, right? We like to count in the decimal numbering system, so we use the symbols 0 through 9 are our 10 unique symbols. But digital computers always use binary. Okay, there's no such thing as a hexadecimal computer. So I've heard people say that, oh, this computer uses hexadecimal. That's not really true. Inside of the computer, it has those transistors which are treating 1 bit at a time. So they're actually binary. But the computer can display for us those binary values in either octal or in hexadecimal or some other sort of numbering system. So when we look at these, the 1 bit is a 1 or a 0 inside of the computer. And so each single 1 or 0 is considered a bit. But we string those together. So when we put them into memory to store these values, to remember them for later, we string them together in groups of 8 bits. And so 8 bits is referred to as a byte. Now, if you remember, 4 bits is 1 hexadecimal character. So to display 8 bits, we need 2 of these hexadecimal, right? 2 hexadecimal values here is representing 8 bits. And so 2 hex values, a lot of times I just shorten it and call it hex, but it's technically hexadecimal. But 2 hex values can be used to display a byte in memory. So I'm sure you've kind of, maybe if you bought memory or bought a computer with memory in it, one of the things they advertise is how many gigabytes of memory it has, or megabytes of memory. If it's a robot controller, they're actually in the megabytes. They don't have gigabytes on these robot controllers, at least not yet. And so a byte represents 8 bits combined together. Now, the original computers, most original computers were like maybe 8-bit computers, and so they called that a byte, and that's what they did. But then when as the computers changed, we went up to 16-bit computers. So in the 80s, we had very common, a 16-bit computer was very common in the early 80s and the mid 80s. And getting toward the later 80s, they came up with 32-bit computers. Okay, so when they went to 16 bits, they started calling that a word. So 16 bits strung together, and a 16-bit computer would be a word. But as we got up to 32-bit computers, and of course now, your typical desktop or laptop computer is actually a 64-bit computer. But so as they went to 32 bits, they started calling those double words because 16 bits was a word. And then when we went to 64 bits, sometimes they call that a quad word, meaning that there's 4 bytes in it. There's 8 bytes in 64, or 4 words, which is why they called it a quad word. But when they do that, you really don't hear people talk about 64-bit. They don't call it a quad word, really. Most of the time, you'll just hear them call it a word because the computer is processing 16 bits in one group, and therefore they're referring to it as a word. And so if it's a 64-bit computer and you hear them say a word, they're probably actually talking about 64 bits strung together in there. But for the purposes of the test, when I say a word is considered 16 bits. Okay. All right, and just to make a note here about the 4 bits, remember that a hexadecimal value, a hexadecimal character, represents 4 bits, and that is sometimes also just kind of referred to as a nibble because 8 bits are considered a byte. So half of that is a nibble. All right. So when we look at this, right, and we kind of already did this when we were counting, right? So as you count, you count zero through in the decimal numbering system. We count 0 through 9, and then we have to move, put a 0 in the ones column and move over to the tens column. When we get to 99 and we want to go to 100, we put a 0 in the ones column, 0 in the tens column, and put a 1 in the hundreds column. And so on all the way up to, as big of a number as you want to write. And so keep that in mind as we try to convert. So how do we convert decimal into binary or binary into decimal? All right, and so the way we do that is basically using these columns here. So if I have this number, which is in decimal, okay, so usually actually we'll put like a subscript here. Call this like base 10, okay, so 25,764 base 10. What that's saying is that we got 4 in the ones column, we have 6 in the tens column, we have 7 in the hundreds column, 5 in the thousands column, and 2 in the 10,000 columns. So what we're doing is we're taking 2 times 10,000 plus 5 times 1,000 plus 7 times 100 plus 6 times 10 plus 4 times 1. Technically, I probably should say times 1 here. 4 times 1. And that gives us this total value of 25,764. All right, so if we wanted to convert a number between decimal to binary, or take a binary number. So let's say that if we already kind of had this number here, say like 1 0 0 0 0. All right, and so what we would do here is we could come along here and we would have like 0 times the ones column and 0 times the 2 column, 0 times the 4 column, 0 times the 8 column, and then 1 times the 16, and that means, of course, we would have 16 then. Okay, so it's actually very easy to convert from binary into decimal. Okay, so this is actually binary to decimal here. Oh, actually not on the slide. All right, so if we wanted to go from decimal to binary, we can kind of do the reverse. So here we have 242. All right, and the way to do this, I try to walk this through for you here on this slide. So we have 242, which is base 10. Okay, 242, which is base 10 or decimal. And we're going to change this into binary. So the way to do that is you want to kind of write this out. So we have the ones column, the twos column, the fours column, the eights column, the 16s column, 32 column, 64 column, 128 column, and the next one would be 2 times that. Notice each one of these, if you start from the right, you have the ones. You always have the ones on the right, and then we're in binary, so we're going to multiply the ones column times 2. So this is the twos column. We multiply the twos column times 2 to get 4. We multiply the fours column by 2 to get 8, 16, 128, and the next one then would be 128 times 2 would be 256. All right, and so my number here is only 242, so I don't need the 256th column. But when you're converting from decimal to binary, you want to find the highest number that you need. And then what you do is you subtract it off. So I'm going to take, my number is 242. So I'm going to take the highest of these, 128, and I'm going to subtract 128 from my 242. And then I'm going to ask the question, is my result positive, okay, or negative? If the result is positive, including 0, then that means that yes, I can do that. So if the answer is yes, I can do that, that's a 1, that's true, and that puts a 1 in this column. Okay, so again, let me just do the one other value here. If we want to one more column out, it would be 256. All right, and so if I take 242 minus 256, okay, the answer there would be a negative. So the answer there would be a negative 14. All right, and so you can't really do that. So the so this value would not be valid, so that you would put a 0 in that location. All right, and so that's what we're looking at. So we would have a 0. I don't have space for it on the slide, but if I do 242 minus 128, and I do that, I do end up with a positive value as a remainder. The positive value is 114. So, I can subtract 242 minus 128 and end up with a positive value. That's what we're looking for. And so if I can do that, then I'm going to get a 1 here. So that puts the 1 in the 128 column. Okay, so we get a 1 in the 128 column. Now I have 114 left. So I'm going to look at the next one. The next one is the 64s column. So I'm going to subtract 64 from my remainder of 114. And I end up with yet a positive value. So I end up with a positive value of 46. And so I put a 1 in the 64s because the subtraction worked. I did the subtraction and I ended up with a positive value. So I put a 1 in the 64s column. Now I've got a value of 46. I'm going to look at the next column, which is the 32s column. I'm going to subtract 32 from 46. That still gives me a positive result, right? 46 minus 32 is a positive 14. So I'm going to put a 1 in the 32s column. Now I've got 14 left. I'm going to look at the next column. The next column is 16. Well, if I take 14 minus 16, that's going to give me a result of minus 2. That's a negative result. So I'm not allowed to do that. Okay, so I'm going to put a 0 in the 16s column, and then I'm going to move to the next column and try to subtract it. So I had 14, and I tried to subtract 16, and I couldn't do that and keep the value positive. And so I put a 0 in the 16s column and moved down to the 8s column. So now I got 14 minus 8. Now that is positive. And so I can do that. And so I put a 1 in the 8s column. I had a remainder of 6 when I did that. And so we go to the next column, 4. So 6 minus 4, that is also a positive result, remaining with a remainder of 2. So 6 minus 4, I can do that. I end up with a remainder of 2. So now I take 2 minus 2. That gives me a 1. I can do that. So I put a 1 in the 2's column. That gives me a positive value. Now, the value is actually 0, right? 2 minus 2 is 0. So now if I tried to take this 0 and subtract 1 from 0, that would give me a negative 1. So I can't do that. So I put a 0 in the 1's column. All right, and that's how we can convert from decimal into binary. It's really quite easy. All you have to do is subtraction. Okay, so the first thing you do have to do, though, is you have to kind of build up. You know, you have the 1's column, 2's, 4, 8, 16. All right, and again, how do you get this? Well, we're doing binary. So you take the 1's column. I don't care what numbering system you're doing, you always have a 1's column. And then you multiply it times your number of unique characters. So this is binary. I have 2 unique characters, 0 and 1. I multiply those together. I multiply binary 2 times 1. So 2 times 1 gives me 2. Now I take that 2 times this column. 2 times 2 gives me the next column of 4. 2 times 4 gives me the next column of 8. 2 times 8 gives me the next column of 16. 2 times 16 gives me the next column of 32. 2 times 32 gives me 64. 2 times 64 gives me 128. 2 times 128 would give me 256. 512, 1024, 2048, and so on. Okay, so you just keep multiplying as you need to. Now, if we try to go to binary if we have a binary number and I want to go back to decimal, we kind of lay it out the same way, but we put the binary number in here, and then all we're going to do is just take these and multiply the binary value times the column it's in. Alright, so here we have this binary value 1001, 1101. So I'm going to put that in here. So I have 1, 0, 0, 1, 1, 1, 0, 1. Alright, so we put that in there with the columns as we did before. And now I'm going to simply just take 1 times 128. 0 times 64, which is of course just 0. 0 times 32, which is 0. 1 times 16. Okay. So we had 128 and we had 16. And then we'd have 1 times 8, which of course gives me 8. 1 times 4 gives me 4. 0 times 2 just gives me 0. And then a 1 times 1, and we just add those numbers up. So we add 128 plus 16 plus 8 plus 4 and plus 1. Add them up, and that gives me 157 base 10. All right, so once again here, we're going to take this 8-bit binary number and we'll put it out here with our columns, 1, 2, 4, 8. Your columns, you always kind of start doing your columns from the right side, and you just multiply times, it's binary, so you multiply by 2. So each column gets advanced by multiplied by 2. So 1, 2, 4, 8, 16, 32, and so on. And then you simply multiply. You're simply multiplying 1 times this column value, or 0 times this one column value. So it's really easy. You don't even have to really do the multiply. you just kind of look, okay, this one has a 1, so we're going to take it. This one has a 1, we're going to take it. This one has a 1, we'll take it. This one has a 1, and this one has a 1. We're going to add it together, and these ones, the values that were zeros, we're just going to ignore any of those. Okay, so we're basically just, it's a true. Remember, a 1 represents a true, so it's like, yep, we're going to use this one, and if it's a 0, it's a false. And then just add them all together. So if you simply lay out the problem like this, it's very, very easy. So again, you start with your ones column on the right, and we're doing binary, so you just simply 2 times 1 gives you 2, 2 times 2 gives you 4, 2 times 4 gives you 8, 2 times 16 gives you 32, 2 times 32 gives you 64, and 128, 256, 512, 1024, and you just keep multiplying by 2. And then you stick in your binary number, and you just find the columns that are ones, and you say, yep, we're going to use those columns, we're going to use these columns, we're going to use this column, any of them that are ones, and we're just going to simply add up that column value. And that gives us our conversion from a binary number into a decimal number. Very, very easy to do. All right, now you could do the same thing to convert between octal to decimal or hexadecimal to number, binary to octal to decimal or hexadecimal. You could lay it out the same way, but I would never bother doing that. Remember that the key to octal and the key to hexadecimal is the fact that they're a one-to-one relationship to binary. So if I had to go from octal to decimal or hexadecimal to decimal, I would first go to binary, because the binary conversion is a one-to-one for every character in binary. For every 3 bits in binary, there's 1 character in octal. Or to say it the other way, for 1 octal character, there's 3 bits. So here is a case where I have, I think, the exact same number I had before there, and I'm going to convert this into octal. So I'm going to convert this now into octal. And so when I do that, now this is a byte, right? This is 8 bits, 2 nibbles. And so when I do that, I need to do 3, to get an octal, I need 3 bits. So you always need to start off on the right when you do this. Okay, so start off over here, and you're going to take the first 3 bits. Okay, and so that's why I put this line here to separate that. And then I'm going to take the next 3 bits, and so there I put that line. Now the problem is I only had 8 bits. So what I did was I added this 9th bit over here. So I added a 9th one because remember, every octal needs to represent 3 bits and a binary number. So when we do that, then now all I have to do is match the chart. So here's a chart where I have, actually technically this should be octal in this case, and this is the binary, so we really don't need this extra 0 in here. Alright, I took that extra 0 in there because we're doing octal, so it's only 3 bits. That was just a copy from the other slide there. But so we have 3 bits here, so now I have the bit 101. So I'm going to come over here and I'm just going to match this. This was just counting an octal and binary, so I'm going to take 101, which is the value 5. So that was from the right side, so the 5 goes there. And then I'm going to take these 3, which is 0, 1, 0. So, or excuse me, 011. Need to say it correctly. So that is a number 3, 011. So that one we put there. And then again, I've already added this extra bit in here, right? Zeros to the left, right? Leading zeros on the left don't matter, okay? They don't change the value of the number. But for binary is representing 3 bits. So I should have 3 bits there at all times. And so we just find the match. Well, that's 010 is 2. So that gives me then 235 base 8, which is octal, right? This is octal. So that's how we can convert from binary to octal. Or the other way, if you wanted to go the other way, if you had this number 235 in octal and you wanted to convert it back, you just write out the ones and zeros based on this chart. Okay? And it's really easy to build up the binary chart. You just start, 000, 001, 010, 010, 011, 100, 101, and so on. All right, so it's just, even if you don't have a calculator handy, it's very, very easy to do this conversion just on a scrap piece of paper. All right, hexadecimal is effectively the same thing, only we're breaking it up into 4 bits instead of 3 bits. So to convert to hexadecimal, okay, and we're actually doing the same number here, but again, we're going to break it up into 4 bits. So I'm putting my divider, so I have 4 bits on this side and 4 bits on this side. But again, when you're doing this, actually always make sure you start counting from the right side here, your 4 bits. Okay, or 3 bits if you're doing octal. So we just write out those 4 bits, or write out all the bits, and then break them up into groups of 4. So we're going to take and break this up into groups of 4. So that gives us a 1101. And then I'm going to come find that over here on the chart, and that gives me a D. Okay, 1101 gives me the D. And then we go and we look at the next value and we find it in the chart, and that of course is a 9. All right, and so 1001 gives us our 9. All right, so 1101 gave us our D. And 1001 gives us our 9. So we end up with 9D. Now I just do want to point out the notation here. A lot of times you might see like a subscript base 16, like I was doing for the decimal value subscripts there before. So we would have like 9D. You might see it written as 9D with a subscript of 16, indicating that it's hexadecimal. Now the only problem with that is in a lot of programming type languages or interfaces, you can't do subscripts. They're not Microsoft Word or some sort of word processor, so you can't do a subscript. And so to indicate that it is a hexadecimal number, you will see one of these 2 notations written here. So you have like 9D followed by an H, where the H implies hexadecimal. Now the problem with that a lot of computer programs will use that to indicate that this is a hex number. So they'll put this H following that. The only problem with that is sometimes the H and the A look very, very similar. And so sometimes people get confused by that and think that the H is actually the letter A, because remember, letter A is a valid character in a hexadecimal number, and so sometimes people would make mistakes there. So a lot of programming languages, instead of you being followed by an H, they put a 0x at the beginning of the number to indicate that it's a hexadecimal number. Okay, so they put a 0 and a lowercase x, and then they put the actual digits of the hexadecimal number in there. And so you may see one or the other depending on the type of program that you're running. So you need to be familiar with both representations. And again, the reason they do that is because the programming tools don't give you the ability to enter in subscripts. And so to indicate whether it's hex or whatever, they either use this 0x at the beginning of the number, or they may follow the number with a H. But again, the H can very easily get confused with a valid number of A and confuse the operator or the programmer. And so that's why I personally prefer this 0x sort of notation. All right, so remember, inside the computer, everything is binary, and the computer's processing bits at a time. So if it's a 64-bit computer, it means that it's got the ability to process 64 bits simultaneously or in parallel. And so there's 64 of those separate circuits in there. All right. But when they're processing things, they're comparing, a bit or a couple of bits together. And so that is done through what's called a logic gate, because it's just simply a 0 or a 1, and you're comparing it to another. So for instance, when you're adding, if you have the binary value 1 1 and you're going to add 1 to it, you have to say, well, 1 plus 1, okay, that's going to be a 0, but we need a carry. So you have to ask the question, do I need a carry? Or do I not need a carry? So we have these logic gates, and the simplest of the logic gates, we have an AND, so 1 and 1, or we have an OR, 1 or 1, or we have a NOT. If it's a 1, make it a 0, or if it's a 0, make it a 1. That's a NOT. And so these then are stored inside of memory locations, and the memory locations are actually built up with they remember what the previous value was, and they're called flip-flops because you can change it from a 1 to 0 or from a 0 to 1. So you can flip it to a 0, flip it to a 1. And so that's why they're called flip-flops. All right, so we use the truth table to describe the logic gates. So the first logic gate is called the inverter, or sometimes called the NOT. So if we have a bit coming into this gate, and it's called a 1, or if the bit coming in, well, let me do it like the table. So this is the truth table here. So we have inputs. We have inputs, In this case, we only have one input, and then we have the output. So what is the output result? So in this case, we have the input, which we're just symbolizing with a letter A to indicate the input. So if the input is a 0, this is going to invert it. All right, so if the input is a 0, we get a 1 out. If the input is a 1, we get a 0 out. Okay, and so that is the inverter circuit. So you can use that to flip a 0 to a 1 or a 1 to a 0. The next one is the AND gate. So with the AND gate, here we have our inputs, which are labeled A or B, so we can have 2 inputs. Okay, you could have more inputs to an AND gate, but you got to have at least 2. And the AND gate says that you must have A and B must be a 1. So if either A is a 0 or B is a 0, the output will be a 0. So you must have A and B to be a 1 so that you get a 1 out. Okay, so that is the AND gate. Now, on top of that, if you threw an inverter after this, then that's going to negate it. So you actually end up a NAND gate here. This little bubble represents the inverter piece. So when we build a gate, a lot of times they have the inverter built right into the gate. And so with a NAND gate, it means you're going to invert the output. So if the result is if either the A's or the B's are 0, if either one of them are 0 or both of them are 0, you get a 1 out. But if they're both a 1, so one A and B are 1, you actually get a 0 out. Now you might say, well, why do we even care? Well, it turns out that when you try to build this out of a bunch of transistors, the NAND gate is the simplest gate that you can build. All right, and so it takes the fewest amount of transistors in a NAND gate. And so it's very, very easy to build a NAND gate. Now when I say that, it's out of any gate that requires 2 inputs. Okay, so I mean, I already showed you the inverter with a single transistor earlier in the lab, right? This was basically that transistor circuit I had shown you before. That's an inverter, and that only takes 1 transistor. But when you're trying to combine two inputs, the simplest electrical circuit you could build would be the NAND gate. And so NAND gates, actually most computer circuits are kind of built out of NAND gates. But I want to point out here that if you do a NAND gate and you just connect A and B together, so you take A and B, your inputs A and B, and you short them together, then you'll never have these middle possibilities, and you actually are back up to an inverter. Okay. All right. So that is the and the NAND. Now an OR, on the other hand, an OR gate says either A or B must be a 1. So if that's the case here, we have if B is a 1, you get a 1. If A is a 1, A or B is a 1, you get a 1. And it also means that A and B, as long as one of them is a 1, you're going to get a 1 out. Okay, so an OR gate is going to give you a 1 out if either one of them is a 1. And so the only time you'll get a 0 out is if they're both 0. Where the AND gate only gave you a 1 out if they were both a 1. The OR gate gives you a 1 out if either one of them is a 1, including if they're both a 1. Okay, and then of course we have the NOR gate, which just negates that. So this was 3 1s, right? If any of them was a 1, you got a 1. So the only time you got a 0 was when all of them were 0. Where a NOR gate gives you a 1 if they're both 0, but is 0 any other time, because you're inverting the output of the OR gate. All right, they also have what they call exclusive OR. So the exclusive OR says that it's only going to be a 1 if one of them is a 1. Okay, so if both of them are a 1, it's going to be 0. So this is a comparison type of gate where you can say, you know, this one is, the B is a 1, but A is 0, or the A is a 1, but the B is a 0, then I'm going to say that's true. But if they're exactly the same, I'm going to give you a 0. All right? And, or you could be, I guess you can ask it the other way, is this different? Are the two inputs different? If the two inputs are different, then your output is going to be a 1 or a high or a true, right? And then of course we have the exclusive NOR, which is the exclusive OR negated. So this is asking, are they the same? So if they're both 0, I'm going to give you a 1. Or if they're both 1s, I'm going to give you a 1. But if they're different, I'm giving you a 0. And so those are the basic logic gates used in building any binary computer type circuit. All right, so here's an example of a flip-flop. This is called the JK flip-flop, and it's made, you can see it's actually made out of 4 NAND gates. But what's happening here is that we are passing the output is Q, and we're passing the output Q back. You see how it's being fed back to the two inputs. So I have my inputs, which they call JK, and we're feeding the input of Q back into the input of K, and we're feeding the Q naught. Okay, the Q with the bar over it is read as the Q naught. And so we're feeding that back into the J. And so the way this thing works, number one, notice the clock signal. So I think I mentioned earlier, right, these computers work on a clock signal. So the flip-flops only change when the clock signal comes through. They're only going to make the change. And the way these things work is that if J and K are both 0, then whatever Q was at the previous clock, that's what Q is going to be on the next clock. So there'll be no change. But if K is switched to a 1, then on the next clock cycle, Q will be 0. And if J is a 1 but K is a 0, on the next clock Q is going to be a 1 out, right? But if they're both tied to a true, if both J and K are a 1 or true, then on the next clock they're going to toggle. So this is like good for counter type circuits. So if you think about, you got parts coming down the line and you want to count them, this is going to send out a toggle. So it's going to go from 0 1 0 1 0 1, and it's going to advance so it's going to toggle back and forth, which is basically going to be counting. Of course we would have to put multiple ones in together, which of course inside the computer we do have that, and we can advance that counter. Okay, so if you think about it, when you're counting in binary, right, you might have something like 0001, and then you go to 10, and then you go to 11, and then you go to 100, and then you go to 101, and then 110. So if you look at like this column, right, this is toggling 1 0 1 0. So you can see here that this is just toggling back and forth in this column, right? So it's just kind of toggling back and forth. So this is would be the counter and this would be the first bit, and then you would actually use this as the clock signal into the next one to toggle the next one, and you could build a counter very easily with these flip-flops. All right, so inside of computers, right, we want to be able to tell these computers what to do. And so to do that, we use what's called a programming language. And it is a foreign language. All right, it's not English, it's a language that we use to give instructions to the computer. And there's several different types, and I've only listed a few of them here. The lowest level one of those is called assembly. Assembly language is basically machine language. You're basically sending out ones and zeros. It's like one step above sending ones and zeros into circuits inside the computer to make it perform the task that you want. So it's very hard to use assembly. Assembly is not used very often anymore to do any kind of programming because it just takes too long to do that. So what we do is we use what we call a higher level language, and then we use a compiler or an interpreter which will convert it into the ones and zeros that we need. Now, probably the three of the most common types of languages are ladder logic. Ladder logic is laid out as it implies in a ladder or rung sort of structure where it performs each instruction sequentially, just like you were kind of climbing down a ladder. You would be processing down the lines of ladder logic, or rungs of ladder logic. They actually call them rungs, just like a rung on a ladder. And so ladder logic is pretty straightforward to read and program, but it's kind of limited in what it can do. The C programming language is extremely common, especially for operating systems and low-level processing, because it's very, very powerful. When you need to, you can get down to the bit level very easily with C, and so you could turn on one bit to tell the robot, for instance, to turn on the gripper and grab something, or let go of something to turn it back off. So the C language is very, very flexible at that level and very powerful at that level. And if you needed to get down into the machine or assembly language level, you can do that right in line in C code very, very simply. And so it's very easy for drivers and controllers, and so it's very, very popular. So we have C, they have C++, which is an object addition to the base C language, and then they've actually also extended that to C+++ here. So they actually had like C++ with a plus below it kind of thing, and so somebody said, hey, that looks almost like C#. If you put the pluses, two pluses right below the first two, it almost looks like a number sign or a sharp sign, so they call it C sharp. And then another language which has gotten very popular is called Python. And so these are just some very, very common programming languages that are available. And then you have, like, most industrial robots actually kind of use what they call a teach pendant language, where you program it with a teach pendant. And so they kind of have their own proprietary language for programming. All right. But there's actually so many different programming languages, I can hardly mention them here. There's R. There's an R programming language. There's a D programming language. There's one called Ruby. Okay, there's called Ruby on Rails, which is kind of an extension of Ruby. So there's like just lots and lots of different programming languages, but these are probably four of the most common for performing any sort of controls type of work in an industrial environment. Plus the built-in proprietary teach pendant sort of languages.